Start recording. Okay. Right. Okay. So what we're going to do today is we're basically going to go through the second part of Bronsted-Lowry acids and bases, and we're going to look at structural features that we can use to determine how strong an acid is or how strong a base is, rather than relying on pKa tables. So that's what we're doing. And we actually got into this yesterday when we were talking about the influence of the atom that is bonded to hydrogen. So the first little bit's going to be a bit of a review. There are two influences. One is electronegativity, and the second one is the atomic size. So in the case of electronegativity, so just as we said after the last question, the strongest acids will have the weakest conjugate bases. And said another way, the strongest acids will have conjugate bases that are stabilized. So if we are looking at methane versus ammonia versus water versus HF, the pKa's are in this range. So methane, pKa is around 48 or 50, depending upon your source. It's super high. So nitrogen, it goes down by 10, and then it's over half, and then here is a big drop off between water and HF. But going from carbon to like methane to HF, there's a massive difference in acidity here. And so one of the ways that you could look at this is if once you remove this proton and you're left with a negative charge, you can ask yourself, well, which of these two negative charges is more stable? Because the more stable negative charge will be the weaker conjugate base, and that will correspond to the strongest acid. So one of the first things we talked about was electronegativity, and fluorine is more electronegative than carbon. So fluorine should be able to stabilize this negative charge way better than carbon can. And so if you've got a choice of stabilizing a negative charge on an electronegative atom versus a non-electronegative atom or electropositive atom, the electronegativity is going to win out. So fluoride is a very, compared to the carbanion, is a far more stable negative charge. So it will be a weaker conjugate base, and that would mean that the acid would be way stronger. So electronegativity. So you can just look and see which type of atom hydrogen is bonded to. And when you're comparing the two, just think which one is more electronegative, and the proton will be more easily removed from the more electronegative atom. So this little trend along the first row of the periodic table goes from left to right. So acidity increases going left to right. Now what we're going to see in the next slide is the atomic size, the trend going down a periodic table. So HF, I should have a little periodic table here somewhere. Fluorine is above chlorine, which is above bromine, which is above iodine. So you're going down the periodic table, and you'll notice that the pKa's really drop off, particularly going from row 1 to row 2. There's a massive drop off here. So HCl is a far stronger acid than HF. And why is this? And I think like you can look at it from the perspective of the bonds themselves, the bond distance being longer between HCl and HF, because the orbitals that chlorine is using to make that bond are further away from the nucleus, so it's a weaker bond. That's one way of looking at it, but it's you have to be careful thinking that way, because the reactions that we're doing deal with their polar reactions, and some of the bond enthalpies that we look at take place for non-polar reactions. So that's how they've calculated it. We'll get into that a bit later on in the class. But a better way to do this analysis is to look at the negative charge and see how it's stabilized. So with fluoride, that negative charge is the valence orbital is the two is the second shell, right? So it'll have all of its 2p orbitals filled, its 2s orbitals filled. So that's basically this Nobel gas configuration here. With iodide, it's way down the periodic table. So its valence shell is, the volume of it is much further away from the nucleus, and there's that one little extra electron, which is basically dispersed in a much larger volume. And so it is, you're stabilizing that negative charge in a larger volumed orbital. And there's a consequence for this when later on in the course when we're talking about substitution reactions, in the sense that iodide, this negative charge is, because it's in a larger orbital, there's very little electrostatic attraction to it from like a random proton floating around in, say, solution. Because it's in a much larger orbital, it's almost like in stealth mode, because that electron can sort of jump around in that orbital, and it's not so big. Where fluoride, the orbital is smaller, so you've got a concentration of a negative charge in a smaller area. So electrostatically, protons can basically just be attracted to it because, well, here's a really small volume with a negative charge in it. Where negative goes to positive, right? So there's more of an electrostatic attraction. So the general trend is when you're going down the periodic table, the atomic size is important, and it's stabilized in these larger diffuse orbitals. Sure. So the volume in these is gigantic, and that was like part of the very first slide we did when we were talking about where the electrons reside in those diffuse orbitals. So as you go down the periodic table, basically, the atomic size, you'll notice here that fluorine is the most electronegative atom we've got. Iodine is far less electronegative, but its acidity is way higher. So atomic size trumps electronegativity. I guess that's the thing we'll talk about. Atomic size is more important than electronegativity, because as you go down the periodic table, the acidity of the corresponding acid increases greatly. So if you think of like one, let's see here. Let's see if I can draw something. Carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur. Okay. Just trying to get. Yeah, so if we're going down I just sort of try to draw a periodic table here. So the atoms that are really important, or the elements that are really important in organic chemistry, we'll see phosphorus a lot, sulfur, chlorine, bromine, iodine. So just remember that sulfur is directly below oxygen, selenium is below sulfur. We don't see that particularly often. So just remember that acidity is going to increase this way and as you go down. So so as the atomic size gets larger, the acidity of the corresponding acid is going to go down as much. Okay, so let me erase this stuff here. It's weird getting there's a part of this which is sometimes it's hard to okay, let's move on to the next question. So the next, I actually got a question here based upon what we just talked about. So if this is your following molecule, where is the most acidic proton? Okay, so let's look at this for a second. Okay, so let's draw our, this little row we had here, nitrogen, and then beside nitrogen, carbon, oxygen. What am I doing? Nitrogen, oxygen, fluorine. And sulfur is below oxygen. So basically we're comparing the proton on the amine versus the proton on the thiol, which one is more acidic. So these are in different rows and different columns. So how would we do this analysis? So if we were to go, if acidity increases this way, and then it also increases this way, oxygen, if there was an alcohol here, it would be more acidic than the amine. But a sulfur would be, thiol would be more acidic than an alcohol. So that would mean that this thiol would have to be the more acidic proton. And so it is it's the most acidic proton. So don't click on the sulfur itself, click on the proton. So the correct response is the proton. So that is the most acidic proton here. And it's basically, if nitrogen and sulfur aren't on the same row or in the same column, you can just move across and then move down, and it'll basically work every time. So right, the thiol will be that proton will be the most acidic. What if it's something like selenium versus chloride? Would it be selenium since the atomic size can? If we are looking at, that's an excellent question. So this analysis basically works very well if you're going left to right. I don't think that HCl is -7 and selenium is SH. I'll have to look that up. I don't know that one off the top of my head. But whenever we're doing an analysis like that, it'll be basically for comparable things. So selenium would be perhaps compared to, say, a hydroxyl group or an amine or something like that. Okay, good. Now, let's see here. I'm pretty sure that, yeah, those are really, okay, here's another question based upon what we just did. So which is the strongest base? Okay, so fluorine, carbon, oxygen are all on the same row of the periodic table. Easiest way to do the analysis of this is which of these atoms is the least electronegative? Which were the negative charges? Is it residing on an electronegative atom, or is it residing on a non-electronegative atom? And so remember, fluorine is the most electronegative. Oxygen is an electronegative atom, not as electronegative as fluorine, but carbon is not. So out of all of these, carbon is the least electronegative, so it's got the poorest ability to stabilize this negative charge based upon electronegativity. So the correct answer is B. It is the least electronegative, so it's least able to stabilize that negative charge, which would make it the strongest base. Fluoride can stabilize that negative charge through electronegativity, and so can the oxygen of hydroxide. So this would be, it's the acid or the conjugate acid to this base. This one would be exceedingly weak. This was relatively strong. This one is somewhere in the middle. So B is the correct answer. Good. Okay, so the second structural feature, which is important besides what the proton is bonded to itself, is resonance. So when we're doing this, we sort of are comparing apples to apples. So we've got 3 different substances here: acetic acid, phenol. So an alcohol attached to an aromatic ring is a phenol, and straight up, this is methanol, just a simple alcohol. The pKa's, when we're looking at them, acetic acid is just under 5, the phenol is just under 10, and the alcohol is very similar to water at around 15.5. So in each one of these cases, it's an OH bond, right? OH, OH, OH. But the difference in the pKa's are enormous. So just a massive difference between methanol and the carboxylic acid. And so why is this? And to do this, what we're going to need to do is we're going to need to remove these protons, and we're going to look at the conjugate base, and we are going to see which of those conjugate bases are stabilized, and in particular, which are going to be stabilized by resonance. Okay, so let's do that. That's what's going to happen on the next slide. So we remove the proton from our carboxylic acid, and we've got the carboxylate anion, and this was one of the examples we did when we were doing resonance structure. So there's a resonance stabilization here where this negative charge is delocalized onto this other oxygen, and they can bring it back to the other oxygen. So this is stabilized by resonance. And also, it's stabilized by resonance, but the formal charge, the minus charge, is on electronegative atoms, oxygen. Perfect. Now the phenol, we did this example as well when we were drawing resonance structures. We can take these lone pair electrons and delocalize them into the aromatic ring. So it could be on this carbon, we can move them over here to this carbon, move it over here to this carbon. And so we've got a series of resonance structures in which this negative charge is delocalized onto the ring. So in particular on this carbon, this carbon, this carbon. So it's delocalized throughout the ring. And our poor methanol here, you notice that this negative charge, it really can't go anywhere. We can't move these electrons here because this carbon's already got 1, 2, 3, 4 bonds, and they're all sigma bonds. So this negative charge is basically stuck on oxygen, which is an electronegative atom. But compared to the other two, where this one's got a series of resonance structures and this one's got 2, that means that this has got no resonance stabilization. So it'll be harder to remove that proton. Now, you might say, well, and if we're comparing the phenol to the carboxylic, to the carboxylic acid, or the conjugate base, the phenolate here, this negative charge, you notice that these negative charges here are all on carbon atoms, whereas the resonance stabilization here is on electronegative atoms. These ones aren't. So this does provide stability, significant amounts of stability. So there's a difference of 5 here. So that's like 100,000 times more acidic phenol is compared to a methanol. But the acetic acid is even more acidic than that. And it's because the conjugate base is stabilized by resonance on electronegative atoms. So that's basically resonance. So it can provide a really massive amount of acidity based upon resonance. So that's an important thing. Now, and remember, in these cases here, we're all looking at OH bonds here. So there's no difference in the type of atom this hydrogen is bonded to, but the acidity goes down markedly. So I've got a question about this. Let's start question. So which of these 2 protons is the most acidic? Okay, so one way to do this is you can draw out the conjugate base once the proton has been removed. So let's see if we can do that. Draw some stuff here. So we got a base coming, grabbing this proton. The corresponding product here would look like this. I'll just draw an R for the rest of the molecule here. And so with this, we can delocalize these electrons into the ring and we can draw a resonance structure. We don't need to draw all the resonance structures. All we need to do is draw one, just so we can show ourselves that this proton, if it's removed, the conjugate base is resonance stabilized. If we were to remove the proton on the other side, we've got sulfur, and it's bonded to a C, H, and then another carbon here. I'll just draw a squiggly line to say something else, negative charge. Now, we can't move these electrons here because this carbon's already got 1, 2, 3, 4 bonds, and they're all sigma bonds. And remember, resonance structures, it's only movement of pi electrons and non-bonding electrons. So there's no resonance stabilization if you remove this proton over here. So, and in each case, it's what we're comparing is an SH bond to an SH bond. So there's no difference in electronegativity or anything like that. So this is purely a resonance. The difference would be purely based upon resonance. So the correct answer is, let's see where everyone did, what the responses were. This proton over here, and so that is the correct one. So this, when this is removed, it can be stabilized by resonance, so it'll be easier to, this proton will be more acidic because the corresponding conjugate base is stabilized by resonance. All right, good. Okay, so we've got atomic size, we've got the type of atom the proton's bonded to, which can be influenced by electronegativity or atomic size. Then we've got resonance. And the third effect is what we call an inductive effect. And we'll see here that the difference for this isn't quite as large as any of the other two. So a prime example is this one with using carboxylic acids. So if you've got atoms that are electronegative, or in fact, if you've got atoms that are pushing, like withdrawing electrons or pushing electrons, these can influence the pKa. So here is an example with carboxylic acid. So a standard carboxylic acid is pKa is just under 5. Once you start introducing electronegative atoms like fluorine, and it's not even close to where this proton is, it's sort of a little bit further away, you notice that the acidity goes down by around 100. So, and that's just because this fluorine is pulling electron density. If you start adding more fluorines, then the pKa even drops even further, so it's now less than 1. So you've increased the acidity of this proton just by adding electron withdrawing groups. And so there's a couple of ways that you can think about this. So if these fluorines are pulling electron density away, so inductive effects, remember, are taking place through sigma bonds. So it's an influence of through sigma bonds. So if you're pulling electron density away through sigma bonds here, that means that this carbon here is developing a partial positive charge, right? And it's going to be shifting the electron density. Let's go back to the previous slide. It's going to be shifting the electron density in this fashion through everywhere else. It's going to be pulling it in this direction. And so the shifting of electron density here is actually going to influence this bond, because now all of the electron density is basically being pulled in this direction. So it makes this bond a bit more polarized, which means it would be easier to remove the proton. And likewise, if you deprotonated itself, this negative charge, so it's got a negative charge here versus a negative charge here, the easiest way to, I think the better analysis is once it's been deprotonated, which one's more stable. So overall, we've got a pull of electron density in this direction, and it's helping to stabilize this. Each one of these are stabilized by resonance, but in this case, it's stabilized. It's this electron withdrawing is making this, stabilizing that negative charge inductively. So, so it's shifted it's made the corresponding bond here more polarized, so it's easier to remove. And because you're shifting all the electron density basically because of these electron withdrawing groups. And so this fluorine is, it's actually interesting. This is used often in medicinal chemistry to help make certain compounds more soluble, or what's the correct term here? Increase the bioavailability of certain compounds. Because this inductive effect can make protons easier to be deprotonated at a physiological pH, which will make them more soluble. So it's a common technique used in medicinal chemistry to introduce fluorines to change the pKa's of certain protons and that type of stuff. And also, fluorine is a relatively small atom, all things considered. So it doesn't get in the way with respect to, because it's small. It's not as small as a proton, but it is a tiny atom, so it's not really getting in the way of things. So it's just this is a common sort of thing with regard to medicinal chemistry. So this is why it's found in so many textbooks, this interesting pKa influence by introducing electron withdrawing groups. Now you can also do the reverse by putting electron donating groups. And if it's pushing electron density in this direction, that would decrease the pKa of that type of proton here. But you'll notice that this effect is far less than resonance. It's far less than electronegativity. It's far less than the atomic size. So this one is probably the least important, but it can be important in certain instances, particularly if you're designing some compound to do something important. So, the final one is the type of orbital, and we can see this when we look at CH bonds. This is particularly important with regard to CH bonds. So when you're comparing acetylene to ethylene to ethane, ethane, like methane, has got a really high pKa. So this is a terrible, terrible acid. It's one of the weakest acids there is. When you're comparing the proton on a double bond, it's not much better. It's a million times better perhaps, but in the grand scheme of things, it's one of the weakest acids there are. But when you get to the triple bond, all of a sudden it's down at 25. So it's an absolutely massive drop off in, these protons are far more acidic. And I tried to write out all the zeros for that. I might have calculated it wrong, but it's just a massive difference in acidity. And what's the difference between acetylene and carbon? And ethane? There's no difference in electronegativity because it's still a CH bond, right? Something's going on. So what accounts for this difference? Each is a nonpolar bond. And the big difference is if you're looking at the hybridization of these two carbons, one is an sp3 carbon, one is an sp carbon. Actually, this is a good question. Is this negative charge stabilized by resonance? Anybody? We've got 2 people are saying no privately. Thank you, Madison. Yes, this is not stabilized by resonance. Okay. But somebody might be thinking, so the answer is no. This negative charge isn't stabilized by resonance. Let's just look at this from a, so if we've got, so one of the sets of lone pairs, one of the sets of p orbitals is in the plane of the blackboard the way I've drawn it, and I've got them overlapping. Now I'm going to try to draw the other set of orbitals that are coming towards us, back into the board. So there's overlap here and back there, and then in the case of the ones in the board, there's overlap there and back there. So that's making our 2 high bonds. These lone pairs that I've drawn are actually in the hybrid orbital of the carbon. So you can't move these to either of these systems because it's in the wrong direction. Remember, they have to be lined up, and this would be 90 degrees. So it's in a completely different environment. So there is no stabilization by resonance for this. But the electrons are actually in an sp orbital, whereas with ethane, this is, of course, tetrahedral. So we will have, I will draw them like this. This will be in an sp3 orbital. Now, the way that textbooks will describe this, so the sp3, this is 25% S, and over here, this would be 50% S. And so if we started with S, an S orbital here and the P orbitals were over here, and we mix them, when you mix them to make sp3 hybrid orbitals, you would have, if this was the energy scale, if this is where the S used to be and this is where the P's used to be, you would have 4 which were basically slightly lower than where the P's were. If you're mixing an S and a P here, the hybrid orbitals would be lower in energy than where the sp3s are. So your textbooks describe this basically as a like, is the electrons in a lower orbital with regard to energy or higher? Let me go back to where I was. How do I get out of here? No, wrong way. Yeah, I don't know how to get out of that drawing scheme. Anyway, I gotta better learn how to do that. So these electrons are actually in a sp hybrid orbital. These ones will be in a sp3 hybrid orbital. These ones will be in a sp hybrid orbital. So sp orbitals have more S character and they're lower in energy. So the way the textbooks describe it is they're stabilized better by the nucleus, because they, remember, a nucleus has got where the positive charge is. They're closer to it, so it's stabilized better. This is not the best. How come I can't erase that? Oh, wrong thing. That's not the best answer, but it is the answer that's textbooks typically say. This is where molecular orbital theory comes into play. If you take Dr. Yan's class, his group theory class, he's going to construct the molecular orbitals of a acetylene type molecule or a ethane, and you're going to see just where the molecular orbitals are and the energy difference between the two of them, and it's a far better basically explanation. But this one's a good one. It's the same sort of thing. sp orbitals are lower in energy, so they're stabilized better by the nucleus. So that's the fourth type of situation. Now this one really is important for carbons, and we're going to see later on that carbon-carbon triple bonds have got they're really useful synthetically, because that proton is so acidic and you can remove it and you can do some fun things with it. That's basically I don't know how to get rid of that empty slot here, but here's a question. Which proton on this molecule will be the most acidic? Okay, so to answer this question, what we need to do is we need to we need to figure out the hybridization of each carbon. So we've got 1, 2, 3, 4, 5 carbons. One of the carbons has got no protons on it at all, so we don't need to worry about that one. And then the remaining 1, 2, 3, 4, we just need to figure out the hybridization. So this carbon here has got one double bond, so it's sp2. This carbon here has got one double bond, so it is sp2. This carbon here has got no double bonds, they're all sigma bonds, so it'll be sp3. And last but not least, this carbon here has got two pi bonds, or a triple bond, so this would be sp. And so that would mean that this hydrogen is in it's using its 1s orbital. This carbon's using an sp orbital to make this bond, whereas this bond, and this bond, the carbon's using sp2 hybrid orbitals, which would be higher in energy. And then these protons here would be sp3 orbitals by the carbon, so that would be even higher in energy. So the most acidic proton is the one right here, and that of course is correct. Excellent. Okay. Right, and now here's my little bit about the hybrid orbital S character stuff. Promoting 18251 group theory with Dr. Yan. Interesting, super interesting class. Highly recommend it. No lab. And it's a neat perspective on how to construct molecular orbitals from really simple systems. It's a great class. So I highly recommend that. Okay, so it's 9:50. No, sorry, 9:45. We've got, I should probably see if anyone's got any questions. Great. Okay, is there any, I could quickly start the Lewis acids and base stuff, but before I do that, there's 5 minutes left. Are there any questions at all? Any questions? Do you want me to start the Lewis acids and base stuff, or do you want to wait till Tuesday for that? Can I explain inductive things again? Yes, certainly. Okay, let's do that. So, right, okay, let's do inductive effects. Okay, so I will draw here. Okay, inductive effects. Okay, so each of these fluorines, sorry, I didn't draw the lone pairs on them, but each of these fluorines are electronegative. So they are generating a overall dipole in this direction, which would look something like this. So they're pulling electron density. So this carbon here is developing a really big delta plus plus. This system over here to the right, so we're in resonance here, right? This is a resonance structure. Oh no, darn it. Okay, let's put a negative charge here. So these electrons are zipping back and forth between they're resonance stabilized. And it's probably even easier to think about this if there wasn't any resonance stabilization here. But overall, this carbon here is developing a partial plus plus because of all these inductive effects. And so it's actually sucking electrons towards it. And so the overall influence of this is that, so when we think about resonance stabilization, the negative charge is being stabilized across a number of different atoms, but it's all through basically pi bonds, right? So to do a resonance structure, it has to be a lone pair electron, and it has to be, you have to have a pi bond. But for when you're shifting electron density inductively, this is like, it's moving electrons within a sigma bond. So the compound which we'd had here, I guess would be CF. So this is stabilized through resonance. The corresponding compound over here would also be stabilized by resonance. But the added thing that this has got going for it is that inductively it's shifting electron density in this direction. And so this negative charge is actually being shared over even more atoms because of the inductive effect. So resonance stabilization stabilizes things through pi bonds. These inductive effects can help stabilize things through sigma bonds, but you can't really draw it with the way that we do Lewis structures, because we got 2 electrons here, we got 2 electrons here, we got 2 electrons here. So but inductively, it's shifting electron density onto this carbon, and we can't really draw it in a good way. We can just you can just think of it being funneled, electron densities being funneled over even more atoms. So if things are stabilized by resonance over by delocalization or more stable, it's a similar sort of thing inductively, but we just don't have a good way of drawing it. So if you've got, say, methanol, and you're comparing the pKa to this to trifluoromethanol, I don't know what the pK is exactly, but just, you can think of it 2 ways. You can think of it from the stability of the conjugate base. So the more stable the conjugate base is, the more acidic the acid will be. But you can also think of it from the perspective of, if this is pulling electron density, this is pulling electron density, this is pulling electron density. So overall, there's a dipole shifting electron density, say over here. That's going to polarize this bond even more. So that proton will be delta plus plus compared to this one, which will just be delta plus. So it's there's 2 ways of viewing it. One is making the little proton more polar, like more naked, I should get way of saying it, because it's got less electron density around it, so it's got a larger delta plus plus. The other way of thinking of it is that it's stabilized, but it's stabilized through inductive effects, so through sigma bonds, as opposed to we just don't have a good way of drawing it. I don't know if that explanation was helpful or not. Is it a little bit better? It's one of the things about Lewis structures, you can't really draw things like an inductive effect. You can't really draw it in such a, but it's basically, it's sucking electrons towards it, and so you're sharing that electron density over more atoms, and that's going to stabilize the system a bit better. Okay, that's good. Thank you. Okay. All right, that's good. Was there any other questions that we can answer? So what we'll do on Tuesday is Lewis acids and bases. That probably won't take a super long time. Then what we'll do after that, we would normally talk about various types of reactions, if my memory is correct. I'll probably try to put up some more. I've got to repost the resonance lecture, the second part to it, and the last week's lecture, which we did using Top Hat. I'm going to basically redo it and post it using Zoom. So it won't be identical, but it'll be a bit better. But I'll try to put out a little review assignment to do through Top Hat. And which will do the review stuff, and then hopefully we can do a little section on acids and bases too. But anyway, if you've got any questions, please let me know, and I guess I'll see everybody on Tuesday. But I'll send you if I post anything extra on Top Hat, I'll send you a little email to let you know about that. Yeah, I gotta stop. How do I stop this?